Today we're going to talk about what happens to the energy as a reaction progresses. Before we do, I need you to get out your reference tables. Open up to table I. We're getting our way through the alphabet, which means we're getting closer and closer to the regions. Reference table. This reference table talks about the heats of reaction, so let me just walk you through this. We have a couple of things. We have some examples of reactions, and then we have what is called a delta H. And delta H is just, what you can remember it as, is it means heat. However, delta H actually is a term that means enthalpy. And enthalpy is just a fancy way of saying heat energy. So you're going to be measuring what's happening to these reactions, whether the heat is going in or heat is coming out. We have two types of reactions. We have exothermic and we have endothermic. And if you look at the root words, exo and endo, exo, like exit, means to go out. So these are losing heat. And endo means heat is going in. Now, with the exothermic reaction, the delta H is negative. And you can see that right here on your reference table, so I don't need to write this down. Review this reference table, commit it, or at least commit some of it to memory. What does this stuff mean? And it's always measured in kilojoules. Okay? So if it has a negative sign, it means that heat is going out. If it has a positive plus sign, it means that heat is going into the reaction or into the system. All right? So what does this look like? First of all, we're measuring it in potential energy, and then it's going to be on the x-axis, it's going to be time. Sometimes they'll call it reaction coordinates. It's just a fancy way of saying time. It's time. So all reactions, all products, or all reactants and products have some form of potential energy. And remember that energy is, potential energy is the energy of position. So with an exothermic reaction, we're going to start out here. This is the reactants. Do another one here. So we have the reactant, and over time, there's going to be a reaction that's occurring. So over time, what's happening is a little bit more energy is required, and then it gives off energy. And this is the product. With an endothermic reaction, it's going to look slightly different. In fact, it's going to look the opposite. So where we start out, the reactants have more energy than the products in an exothermic reaction, and the reactants have less energy than the products in an endothermic reaction. So one way to think about this when you're looking at these problems is you always want to think about some guy rolling a ball, some person rolling a ball. Could be a man or a woman, or rolling a big stone over a hill. So the amount of energy that it takes to roll that ball or get that ball rolling on its own is called the activation energy. And if you look here, the activation energy is measured in green. So this guy has to roll the ball this high in order to get the ball to roll on its own. This is the activation energy. The activation energy for an exothermic reaction is less relative to the activation energy of an endothermic reaction. Now when we look here, the endothermic activation energy is again the same amount of energy it's going to take this girl to roll this ball up the hill. For our purposes, the activation energy for an exothermic reaction is typically less than the activation energy for an endothermic reaction. One other thing that you need to know is to calculate the delta H. If you're given a problem like this and you're given numbers on the side, you know, you have an axis or whatnot, you're going to take the H of the product, in other words, the energy of the product, and you're going to subtract the energy of the reactant. And that is considered the delta H of the reaction. And sometimes you'll see reaction abbreviated RXN. So if I look here, let's do the same thing, this delta H of the reaction. So if I look here, this number right here is lower than this number. So let's just assign an arbitrary number. Let's just say this is 1 and this is 5. The delta H of this reaction is 1 minus 5. We do not pay attention to the activation energy. Product minus the reactant. 1 minus 5 is -4, and it's typically measured in kilojoules. Let's say it's the same thing. Let's say that this number is 2, and let's say this number is 5. So I'm going to take my product minus my reactant, or 5 minus 2 equals 3. This is 3 kilojoules. Endothermic, positive. Exothermic, negative. One thing that's going to make this reaction easier is the use of a catalyst. And what a catalyst is, it is a substance that provides an alternate pathway for this reaction to occur. So it's typically speeding up the reaction. A very famous catalyst, or a famous type of catalyst that we've all talked about in living environment, are enzymes. Enzymes speed up reactions that would normally take a lot longer. And what the enzymes do is it's providing another path for this reaction to occur. And a good way that you can think about an enzyme or a catalyst is it's like a shovel. So to get this ball over the hill, you still got to roll the ball up a hill, but you don't want to roll it that much. So you get a shovel, and let's say you dig out a path. So there we go. My activation energy is no longer it's no longer very high, but my activation energy is actually quite low, meaning that this reaction is going to go relatively fast with the catalyst. So again, think about it. A catalyst is like a shovel, lowering the size of this hill and allowing the reaction to occur more rapidly. You're not going to see it drawn like this though. The way you're going to see it on the test is you're going to see it like this, and then you're going to see it like this. And it's going to ask you to compare the difference in activation energy with and without a catalyst. And they might label this with catalyst, and this one will be without catalyst. Same thing